Hello ladies and gentlemen, I am Dr. Claudia Albers, Planet X researcher and professional physicist. And today I'd like to bring to you another one of my articles. This one is entitled Stellar Core in Lasco C3 Image Has Comet-like Characteristics. And in this figure below we see a faint object. It's in a Lasco C3 image from May 20th, 2018. And as you can see, the object's angular width is about 2.5 times that of the Sun. So that would be the white part. And the Sun's size is indicated by the white circle on the coronagraph occulter. So that white circle there. So this is about 2.5 times larger than the Sun. Now the object seems to have developed comet characteristics, namely a coma. This gaseous part, it looks gaseous, diffuse, it's obviously emitting light, that's why it looks white, and two comet-like tails. Now, although these seem to be much fainter than what is usually seen in comets, and we know these are tails, not trails. If there was one of them, might be confused with a trail that the object's leaving behind, in other words, leaving material behind, but that cannot be because the object could not get to this point through moving from two different directions. Have to move from this direction and that direction at the same time, and that's just not possible. So what this is the object is pulling material in towards itself, and this is what causes comets to produce such tails as well. Now the object always also has what looks like a dark circle in it, and it seems to have a darker trail within the white tail. So the circle, as we will see, will give us a good idea of the actual size of the object. So the faint trails, let's start by calling them tail, behind the object seem to be comet-like tails. These will be due to positively charged material drawn from one of the Sun's nebula clouds. The material is drawn in towards the object, whilst the current of electrons is drawn from the Sun's corona. The two currents meet at the object's surface and give rise to a cloud of material which emits light around the object, and which is called a coma. The coma may be many times larger than the actual comet nucleus. In this case, it appears to be only 2.5 times larger. The electrons will also combine with the positive ions in the tail. Whenever positive ion captures electrons, photons are emitted, so that's why it looks white. Photons are being emitted, visible light photons. Now, it is these photons that cause both the coma and the tail to give off light, and you may look at Article 170 entitled Comets, Planets, and Crustal Displacements for more details on that. The dark circle indicates the size of the original object and the fact that it is absorbing electrons coming from the Sun, leaving less electrons to combine with the positive ions coming from the Sun's nebula clouds, and thus producing both a surface and a region within the tails from which less photons or no photons are emitted. And this is what a comet usually looks like. As you can see, it has very bright tails. The tails always point away from the Sun because they are created due to material that the object attracts towards itself from the Sun's nebula clouds. So these are clouds or rings containing positive ions that are emitted by the Sun in the solar wind and end up in these rings. Just like Saturn has rings, the Sun has rings or nebula clouds around it, but the Sun is a much more powerful star than Saturn, so it has a much larger ring area or capacitor. I call it the solar capacitor, but James McCanney was the one who first called it by that name. So what we have is positive ions coming in from the sun's outer nebular clouds, and they are electrons coming in from the sun's corona. And this occurs because the object, like all objects in the universe, from atoms to stars to galactic nuclei, have a negative outer layer which attracts the positive ions, which then attracts the electrons. So we have a current coming in towards the object. The electrons and the ions meet at the surface, and the ions start capturing some of these electrons. When they do, photons are emitted. And then once the atoms are neutral, there will be chemical reactions. So for example, hydrogen will interact with oxygen, create water. And that's why we often see water in comet tails. The electrons will move beyond the surface into the tail region and interact with the ions in the tail region, also leading to light emission and the production of molecules like water and sulfur dioxide, things like that. Now this also occurs because the object is following an elliptical orbit. Objects, even though they have negative outer layers but follow circular orbits, will not pull a current from the solar capacitor because they will stay within the same potential, electric potential. So it requires a change in where the object is in space that has a different potential for it to draw a current from the solar capacitor. So the object in the Lasco C3 image above is not as bright as normal comets, suggesting that it does not draw as strong a current as a comet would. This indicates that it does not have a normal outer negative layer of electrons, which suggests that it is a stellar core, since these objects are known to be depleted in electrons and act as superions, whereas normal celestial objects such as the Sun and its planets and even asteroids will act as super atoms or super neutral atoms. And you may look at Article 193 entitled Stellar Cores in the Sun's Corona. Why do they not collide with the Sun? And here's another illustration of what occurs with comets. You can see the coma, you can see the tail. Positive ions are coming in. The electron current is coming from the Sun's corona, and they will meet here, produce the coma. The electrons will keep on moving into the tail region, and they will interact and produce light, and chemical reactions will occur as well. Now here we see Comet ISON in several images. The most interesting is, of course, the Lasco C3 image. You can see that it produced this type of tail. The coma was not spherical. So the fact that the current object has an absolutely spherical coma suggests that this particular object is perfectly spherical and very large. And of course, most comets are small and are just like asteroids, so they have far from a spherical shape, so they will not produce a spherical coma. But the current object obviously seems to produce a perfectly spherical coma, and this is not the only time this type of object has been observed. They were also observed, and there's more than one here, in 2009 and 2016. This one is from February of 2016. As you can see, one of these objects is very bright and therefore must have a stronger outer electron layer, so it has a more negatively charged layer. It still has a dark surface, which means that it's still absorbing electrons, so it has not absorbed as many electrons as it needs to counteract the positive core. But it is brighter than the one in the 2018 image, so it most likely had more electrons than the one we are seeing in the 2018 image. But this object was not alone. It was accompanied by this one, which produced a very faint trail. And this one was obviously extremely depleted in electrons. It's hardly seen at all. Of course, when these objects first come into the solar system, they are not seen at all. They do not emit any light whatsoever. And they do not draw a current from the solar capacitor because they don't have electrons in their outer layer. They have a neutral outer layer. And here we see two of these objects as well, as you can see, producing the same type of trail but fainter. So these are possibly newer arrivals in the solar system. They are also not aligned with the sun. As you can see, these two are aligned with the sun. In other words, the negative currents coming from the sun, the layer points in the opposite direction, but these two are not. And of course, it's likely that they are able to draw electrons not just from the sun, but from other objects that may have arrived before and may now have quite a lot of electrons in their outer layer, other stellar cores that are around the sun. And it seems that they are interacting with one of these here because they are not aligned with the sun in this image. They are possibly aligned with another object that's just behind this darker region that is always in these images. There's even what seems to be some light emission here that may be coming from that object that is just behind here, and that these objects are possibly drawing electrons from it. So an object which absorbs electrons will be depleted in electrons, which the stellar cores that have invaded the solar system are known to be. So the object in figure 1 and the objects in the above images therefore appear to be more objects belonging to this system of invading dead stars, which come from the sun and absorb energy from it. And we see one of these objects in an SDO image drawing material from the sun. This is the main way they draw energy from the sun. This material will have protons in it. It will have a lot of gravitational energy, which is in the form of photons within that matter. And the object draws that and draws gravitational energy that way. Most likely will draw electrons, first of all, when it first makes contact with the sun's corona. And this is possibly the way they are causing the sun to go dark for certain periods of time. When they make contact with the sun, they draw on the sun's outer layer of electrons. When that happens, the sun's driving electric potential drops, and because the sun's an electrical object and emitting light, due to that electrical potential, it stops emitting light, it goes dark. And the previous article I have written was about that, about the fact that the sun goes dark and what are the implications. Now, comet tails always point away from the sun, and according to James McCanney, are very narrow when the comet is far from the sun, become very wide when the comet approaches perihelion position. So this is the reason why it looks like there are more than two tails. It develops, it's very wide, it's possibly coming from two different nebula cloud regions, and they become wide like this. And then the electrons come in and start interacting. Some of the electrons will go this way, some of the electrons will go that way, as they are pulled in towards the positive ions. So this is an illustration of what these comet tails will look like when a comet approaches perihelion. This is not a comet, but it is drawing current from the solar capacitor, like a comet would, because it has developed some a weak, although some outer negative layer. So as you can see, these tails point outwards from the sun, somewhat like these ones here. So this is possibly this one points further up, so the object may be here somewhere, either slightly behind the sun or right next to the sun, as far as its perihelion position is. So this object must be very close to the sun at this moment in time, and this means that we can actually do a direct size comparison with the sun, and we can see therefore that it's likely to actually be 2.5 times the size of the Sun, at least the comet is. And the object itself, indicated by this dark circle, is about the same size as the Sun. Now, the object of interest, therefore, as I said, must be very close to the Sun, and therefore it's about the same size as the Sun. And these objects are likely to be very close to the Sun as well. As we know, stellar cores come very close to the Sun. They come so close to the Sun that they go into the Sun's corona and make this kind of connection. This one here is about half the size of Jupiter, but we have much larger ones that have come in. And these objects interact gravitationally with the Sun in a very, very weak manner. So their gravitational attraction is very weak. They come to the Sun through the electric interaction. They are electrostatically attracted to the Sun. The gravitational interaction is very weak. Now, so one of these objects in the 2009 is brighter than the one in the 2018. As you can see, this one's brighter, but the others are fainter, suggesting that the stellar cores associated with these fainter tracks were more depleted in electrons than the stellar core producing the brighter track. Now, stellar cores are explained in Article 184, entitled Stellar Core Evolution, as arriving in the solar system so depleted in electrons that they have a neutral rather than a negative outer layer. And this is a diagram from that article that illustrates the evolution of a star into a dead star stellar core. And you start out with a star that has a full amount of gravitational energy. It's able to generate a lot of gravitational energy, and this is done through decay of unstable nuclei or fission in the core. And it has a full complement of electrons, although stars will continuously lose electrons. They will move out with some of the ions that move to the Sun's outer layer, and from there, because they are weakly attracted, will leave the solar system and move on into the galactic or intergalactic space, or interplanetary space first, and then into interstellar space. So as the years pass, the star will lose the ability to generate as much gravitational energy in the core, so the electric potential between the core and the outer negative layer decreases, and eventually a point is reached when the star is no longer able to emit light. And because the gravitational attraction decreases because of the loss in gravitational energy, the star will also increase in size. And at the same time, the star's effective mass, that is its ability to draw other objects gravitationally towards itself, will decrease. So it'll grow in size and seem to have less effective mass. At the same time, it will continue to lose electrons. Eventually, it reaches a point where it hardly generates any gravitational energy. It will still most likely maintain a positive core for a while, but it will be completely depleted in electrons. And as the potential decreases, the electrons will start moving inwards, so it becomes more neutral as well. And eventually the outer layer becomes completely neutral. There are no negative electrons there. So at this stage, it has become a stellar core. But it's a positive object, and it will be attracted to the negative outer layer of other stars or the galactic nucleus. These dead stars are actually supposed to move back towards the galactic nucleus for reabsorption, and obviously a system of these objects have encountered our Sun and were attracted to the Sun, to its negative outer layer, since it still had a full complement of electrons there, and they've come in, they've moved into the Sun's corona and started absorbing electrons and gravitational energy from the Sun. So as we can see, this is illustrated here. Our stellar core is a positive ion, or a positive super ion. It's attracted to the Sun's negative outer layer. So it's the electrostatic attraction that brings them to the sun. The gravitational attraction, there is still some, but it's very weak. So in the initial state of electron depletion, stellar cores will not draw a current from the solar capacitor. But once they make contact with the sun's corona, they will draw electrons from the sun and start replenishing their supply of electrons, whilst causing the sun to become depleted. Initially, the electrons they will draw will move below the surface toward the inner core, but eventually, as the object gains gravitational energy by drawing matter from the sun containing protons, it will be able to start forming a negative outer layer of electrons. Once this negative outer layer is in place, the stellar core will be able to draw current from the solar capacitor and will thus produce comets and comet-like tails, as seen in the image in figure 1. Now, the fact that it produces a dark tail indicates that it is still absorbing electrons, and that the process of absorbing enough electrons may take a very long time. In addition, since they will most likely draw electrons from each other as well as the sun, it is possible this process will never be complete, as new objects seem to continue arriving in the solar system, and they will thus continue to draw electrons from the sun indefinitely until the sun has no more to give. Now, comets would not produce a dark trail because they arrive in the solar system with no electron depletion. In other words, there are enough electrons in the outer layer to cancel the positive charges on the inside, which is analogous to them being a neutral atom, which has enough electrons in its outer shells to cancel the positive charge inside the nucleus due to the protons present there. And this is illustrated here for a lithium atom. A neutral lithium atom has 4 protons in the nucleus and 3 protons in the nucleus and 3 electrons in the outer shell. So it's neutral because there are as many negative charges as positive charges. But if this lithium atom was to lose one of its electrons, then it will become a positive ion, because then it has one more positive charge than negative charges. And the way this would occur is if it absorbs a photon, and a photon is gravitational energy, and the moment this electron absorbs a photon, then the repelling gravitational interaction between the proton and the electron, which is opposite to the electrostatic interactions I explained in previous articles on gravity, then this repelling force increases, and when it increases, the electron either will move away from the nucleus, it will move to a higher orbit, or it will exit the atom completely. And when it does, this atom becomes a positive ion. So it's actually photons or gravitational energy that causes electrons to move away from the nucleus of an atom, and to also move away from the positive core of a celestial body and move to the outer layer. And this is why all objects then have outer negative layers. It is actually because of the gravitational interaction and the fact that there is gravitational energy being generated in the core. So in conclusion, the object seen in a Lasco C3 image appears to be a stellar core which, although still depleted in electrons, has been in the solar system long enough to have developed an outer layer of electrons, so that it is now able to draw a current within the solar capacitor and thus produce comet characteristics, namely a coma and tails. The dark track indicates that the stellar core is absorbing electrons coming from the sun's corona and are still in a depleted state. In addition, the object must be following an elliptical orbit, as objects in circular orbits will not draw current from the solar capacitor. And these are the references. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.